Hello everyone, my name is Louisa. I'm a PhD student at the University of New South Wales in Sydney, Australia. And today I'm going to be talking to you about the work that I've been doing looking at how the intracluster light fraction can vary across different cluster redshifts and different cluster environments. So Anthony's already explained a lot of introduction about the ICL, but in case you forgot, I will go over it again. So if we take a lovely deep image of a galaxy cluster and we mask out all of the brightest parts of that cluster, what we are left with is this diffuse low surface brightness light that we can see extending throughout the center of the cluster, around and between all of the different cluster galaxies, and that is the intracluster light, or the ICL. So it's stars that are not bound to any particular galaxy in the cluster, but float freely within the center of the cluster potential. So what do we know about the ICL? Well, we know that it's produced through the tidal stripping and merging of galaxies as they come together to assemble into a cluster, and that cluster evolves over time, as you can see happening in that GIF on the left there. So if we study it, the amount, the distribution, the colors of it, we can actually use it to trace the history of the interactions that have occurred within that cluster in the past. It also makes up a very significant portion of the cluster's stellar mass, in some clusters by some estimates up to like 40%. So what we know about the ICL tells us that it is a really significant and very interesting component of a galaxy cluster to study if we want to know more about how it and those galaxies have evolved over time. So what don't we know about the ICL? Well, a lot of different things about the specifics of it. But mainly they can kind of be grouped into two big questions. The first one is, how does the ICL form and grow within these clusters? And of course, linked to that question is, what can the ICL tell us about those clusters that we find it in? So in order to answer these questions, what we really need are very large samples of intracluster light measurements. The formation of the ICL is a stochastic process because it's tied to galaxy interactions. And so in order to disentangle all of these trends that we're seeing, we really want to compare the amount of ICL in a large variety and a large number of clusters. Historically, this has been very, very difficult for kind of two main reasons. The first one is that the ICL requires very deep imaging. Luckily for us, with Euclid and LSST and Roman, there is lots and lots of this kind of data coming, so that point is kind of covered. But the second problem is that historically it has been very, very difficult to scale most measurement methods of the ICL to these enormous amounts of data that we're seeing. And here I'm talking about measuring the ICL fraction. So that's the proportion of cluster stellar light that's contained within the ICL. So to kind of address this second point, in my previous work, we trained a machine learning model in order to importantly mimic human measurements of the ICL fraction. So there isn't really a ground truth of the ICL fraction. You can ask me about that later. So in this case, what we did is trained it's a convolutional neural network that will take in images of these galaxy clusters and output a probability distribution of what it thinks a human, namely me, would measure the ICL fraction to be within that image. I'm not going to go into more detail here, but if you are interested, there is the QR code for the paper there, or you can just ask me about it. I could talk about it for a very long time. But this model is able to perform accurate measurements of the ICL fraction automatically, which allows us to process large ICL samples much more quickly than we were able to before. So the sample that I'm going to be talking about today is HSC SSP imaging. So we have sort of two cluster samples. We've got chimera clusters, so that's a photometric red sequence cluster finder, and this gives us 101 clusters. And these are the clusters that the model was initially trained on, and you can see the performance of the model on predicting those clusters' ICL fractions in the blue points on that plot there. And we also added another 76 groups identified by the gamma survey, so from the overlap between gamma and HSC imaging. And these are previously unseen images by the model. So the model is just run on these groups and clusters. And so in order to check that the model is performing okay and not doing anything super weird with these unseen images, we manually measured 10 of those in order to check how the model was performing on them, and those are the red points on that plot you can see there. And so what we find is that the scatter in the model's predictions on these unseen gamma groups is identical basically to the scatter that it had on the Chimera cluster. So that indicates that the model is performing well on these unseen images. So the big question that we're trying to unravel in this study is how is the amount of ICL varying within these different clusters? So in order to look at this, we're going to be looking at redshift. So we use spectroscopic redshifts if we have them, photometric redshifts if not. Halo mass, these are halo masses calculated from scaling relations, which are both calibrated with weak lensing, and the magnitude gap. So that is the difference in magnitude between the brightest and second brightest galaxy in the cluster. So you can imagine if you've got two big bright galaxies, the cluster is likely to be in an active merging state, whereas if you have one big BCG and a lot of little tiny satellites, the cluster is likely to be relaxed. So using these parameters, we're looking at how the ICL fraction is varying over time across different kinds of environments and different cluster dynamical states. And this is going to allow us to put a couple of puzzle pieces into this big question of how is the ICL forming and growing within these clusters. Okay, so let's look at redshift first. So one thing to note here is that we make a cut in our sample in order to remove the excess correlations of redshift and halo mass and redshift and magnitude gap. So what you're seeing there is just the effect of redshift on the ICL fraction that we're measuring there. And what we see here is that there is a significant decreasing trend with redshift, with a Spearman correlation coefficient of negative 0.6-ish. So that indicates that clusters at higher redshifts have lower ICL fractions than ones at lower redshifts. Now, the question that we have to ask, because it is redshift, is does this indicate that the ICL is really building up over time, or can we actually explain this effect just through observational effects? So in order to look at this question, what we did was model a cluster. In this case, it was Abel 85, because we have Sussex parameters for the BCG, ICL, and cluster member galaxies. And then we asked the question of what would this exact same cluster look like if we had observed it at different redshifts. So we rebin the image, we apply surface brightness dimming, we de-age the stellar populations, and you can see here the result of redshift 0.1 on the left all the way up to redshift 0.5 on the right. And so obviously we can see by eye that the cluster is dimming as it goes up in redshift. The ICL and the galaxies are of course dimming by the same factor, but the problem is that because the ICL is so diffuse and faint in this image, that as we go up and up in redshift, we're actually losing more and more ICL below the surface brightness limits of the image, even in an image as deep as we get with HSC. And so if we do this and we measure the resulting ICL fraction, what we find with different starting ICL fractions on those yellow points there is that we can actually kind of, the trend that we find actually kind of matches what we are observing in our real data, which is underneath. And so what we're finding is that the ICL fraction redshift correlation that we are observing in our real data is actually kind of plausibly explained by these observational effects, even though this is just a very simple model so far. So what this indicates is that potentially we're seeing little to no buildup of ICL over time within these clusters. Moving on to halo mass. So we make a cut to remove the correlation between halo mass and magnitude gap. I can't show you a pretty picture with just the effect of halo mass because its correlation with redshift is too strong for me to take it out with just a cut. But I've got this one where I have binned it into smaller redshift bins so you can kind of see a bit more what's going on there. And so what we do here in order to remove this effective redshift, to control for it, is a partial Spearman correlation. And once we control for redshift, we do still find a significant decreasing trend between the halo mass of these clusters and their ICL fraction. So this means that what we're seeing is we're seeing slightly higher ICL fractions in group environments as compared to cluster environments. Finally, moving on to magnitude gap. Again, we make a cut to remove the excess correlations with halo mass and redshift. And what we find is a marginal positive correlation between the ICL fraction of these clusters and the magnitude gap, which again is a proxy for cluster relaxation. You can see that the relationship has a lot of scatter there. Part of that is probably due to the fact that magnitude gap is not a perfect proxy for cluster relaxation, but it could also be that the effect really is quite weak. However, you can see in those bin points there as well that there is a kind of weakly increasing systematic trend that we're observing within this data. So this indicates that the relaxed clusters in our sample are more likely to have slightly higher ICL fractions than the non-relaxed clusters in our sample. Okay, so what do these points all mean for how the ICL is forming and growing within these clusters? So what this means is that the ICL could be forming in these clusters mainly through galaxy-galaxy interactions such as tidal stripping, because this would make the production of ICL more efficient in lower mass halos because of longer interaction times in those halos. And so that would give us the effect of having slightly higher ICL fractions in groups. What this would mean as well is that the ICL is building up slowly and consistently within these clusters in the absence of recent mergers, which would also gel with what we're seeing with the cluster relaxation trend. However, once we control for these effects, what we're finding is plausibly no preferred epoch of ICL formation. So no redshift where ICL production is more efficient than others, although again, it was quite a simple model, so more work needed there. What we really need is a lot more data, which we will get, and also measurements using the different methods that are available to measure the ICL fraction. Here, I've talked about one specific one, but there are a lot of different methods and they all come with their own different systematics and biases and assumptions, and so it's really important to get a full overview of what's going on with other methods as well. There will be a paper coming soon in that it does exist and people have seen it, but it will be out at some point. And yeah, that's all. Thank you.
Questions for Lisa?
So you chose a fixed surface minus to mask.
Sorry, could you say that again?
Did you choose a fixed surface minus to mask the chaos?
Yes, so yes, I didn't talk about it here, but the measurement method that I was using is the surface brightness cut method. So essentially what that does is it just says everything below a surface brightness threshold of, I use 26, but you can use 25 or 26.5 or a lot of different things. I count that as ICL. So it's kind of one of the simpler methods for distinguishing between the ICL and the cluster galaxies.
Right. So how does the fraction depend on this choice?
Very significantly is the short answer. I am not sure yet about. One thing that I'm really interested in is how the different choice of measurement method could be affecting these trends, like the actual overall trends that I'm observing in these clusters. Because, like, for example, something that I would be thinking about is that different portions radially of the ICL might be coming from, say, different formation methods. And so if you use different measurement methods which would probe different areas of the cluster better or worse for ICL, you might actually draw different conclusions about where the ICL is coming from, for example. So the main limitation of the surface brightness threshold method that I'm using is that you miss all of the ICL that is in projection with the BCG and in projection with the cluster galaxy. So that's cutting out a lot of ICL which is very close to the center of the cluster. And so that could be having an effect in terms of what what kind of ICL I can probe with this method.
One quick question from James.
So ICL fraction varies a lot cluster to cluster, that has been confirmed by simulations or observations. But one interesting thing is that your mean ICL fraction is systematically lower than what's reported in the literature. Do you think that comes from the surface brightness cut method you applied?
Yes, I think that, so the mean ICL fraction that I'm finding in my data is pretty comparable to other studies that have used the surface brightness threshold method. If you consider all of the, like a lot of other studies that use different methods, their mean ICL fraction tends to be a lot higher. And again, I think that's just because of the ICL that's lost by the method in projection with the cluster galaxies.
Thank you.
Okay, we should move on. So let's thank Louisa again.